Okay, welcome back. We're just going to try and finish up the last part of this 1.1 lesson, and then hopefully you kind of understand the concepts there and you did some of your practice work. So you should be equipped to move on to 1.2 on scalars and vectors. But let's finish off a few more questions here. So describe the following motions from the graph. So look at this graph here. Now, distance and time can be kind of generic. It doesn't matter whether it's meters and seconds or kilometers and hours. It's just the shape of the graph that's shown here. And so when I look at it, I kind of like to divide it into three parts when I notice the graph is very constant in one location here, and constant again in this location, and finally constant in this location as well. So when I look at this, I break it into three main parts to it. Okay? So when I look at this first part, I can see that, number one, I started at this location. I didn't start down here at the origin. So I must have started away from my reference point. And because the line is very straight, that indicates uniform motion. So in part one, we're looking at the idea of uniform motion, moving away from the reference point, but not starting at the reference point. So you start away from the reference point, or some distance, now the reference point is going to be used a few times in this, so what I want to do is I want to use some way to think about it, okay? So I'm thinking about this location right here being the reference point, so maybe I'll use RP for reference point. And when I want to write reference point, I don't have to write the whole thing out. Okay, so some distance from the reference point, then moving away at constant speed. Okay, and then take a look at part two here. We talked about this last slide, so you probably understand the fact that there's no motion, you're not moving any distance, so at rest, okay? And then part three, here you notice the slope is down, is in fact a negative slope, and you're moving back to the reference point at a higher rate of speed. That's what's happening because the line's steeper, okay? So steeper line than part one, so we're moving back to the reference point. At a higher rate of speed. Or just simply higher speed. All right, down below here. This one right here. It's just trying to get across the idea with, the rate of motion here with these lines and what direction's happening. So in part one, you can see that it's moving away from the reference point fairly quickly, okay? And in part two, you're moving slowly back to the reference point because the line is just much more gradual slope, okay? So it's more gradual slope, so moving more slowly back to the reference point. I hope you're getting the idea here. All right, moving along to this next little question here where we're going to do a little more graphing. Now this one here shouldn't take much time, but what we're trying to do is we're just trying to plot a graph trying to show where something is essentially moving at a given speed here. But what we're going to do now is we're going to make a different kind of graph. We're going to make what we call a speed time graph. Okay? A speed time graph means that we're going to want to have speed on the vertical axis and time on the horizontal. And so when I put my time in here, I might just go by fives or something like that for simplicity. So 1.0 here, 2.0 here, 3.0, 4.0, and 5.0. So it's a simple graph to make, as I was mentioning, but the idea of now we're moving at a constant speed. So we're going pretty fast for 5 seconds. In fact, 4.5 meters per second. So graphing this, I'm just going to kind of get my scale set up for the 5 seconds here. I might just go by 4s for simplicity. So I've got 1, 2, 3, 4, and 5. Now we're moving at 4.5 for all the given time there. So we're looking at from 0 to 5 seconds at 4.5. So let's plot the graph. I'll just do it in different colors so it stands out a bit. Always get some pride in your work, okay? At 1, we're at 5 in here. So that little circle was kind of off. My apologies. And there we go. Always making a line of best fit. Of course, these graphs generally are set up so that it's not much experimental data. It's just a constant kind of thing. And you don't have to make it go past there if you don't want. You can go just up to the 5 seconds if you like, and because we don't really know what the motion's going to happen after that unless we're told something else is going to happen. Okay? Now it says here, right, when there's uniform motion, the shape of the speed time graph. Okay? So uniform motion, the shape of a speed time graph is going to be a straight or horizontal line. Slope of the line is 0 because the velocity is constant. So if I did do a calculation, I'd find that there's no rise to the time, which would be the run, and so the ratio would be 0. The slope of a speed time graph will tell you the acceleration, though. So if there is an object that's speeding up, for example, then when you calculate the slope, you're going to get the acceleration. If it's a 0 value, there's no acceleration, like in the example I just did. Now the formula we use for acceleration, though, is the change in speed over the time interval of the change in time. And this is the formula that we are going to use, probably similar to the one on your data booklet. Now there's some practice problems I want you to try out, and then we're going to take it from here tomorrow. Thank you for joining me. Goodbye.